This video is on thermodynamics, which is about the loss or gain of heat energy during a chemical or physical change. Now, you might remember this potential energy diagram. It's very familiar to you. There were the reactants on the left right here, and you had your products on the right. Then you had the hill in the middle of it. All right, before we get started, let's take care of one thing. I don't care about the hill in the middle. All right, the hill in the middle has to do with what's called kinetics. I'm just kind of getting this out of the way right now. Kinetics has to do with the rate or the speed of the reaction. All right, and that has to do with something called mechanism, which means what are the steps in the reaction. So sometimes the reaction has one step, like we showed you in 10th grade. Sometimes there's 3 steps in a reaction. All right, each of which has their own activation energy, their own activated complex. Ignoring that, all I care right now about is the difference between this plateau and this plateau, which in 10th grade you called delta H, but now I'm going to call delta E. And it's important to make a distinction between the two of them. Delta H, which we're going to use primarily here as well, but you need to understand why it could be delta E, is what you get when you do what's called constant pressure calorimetry. The big idea is essentially this: energy can be lost in the form of heat or work, or can be gained in the form of heat or work. However, if you do the chemical reaction in a container whose volume is constant, like a rigid container, then any work that would have been done by expansive gases is not allowed to happen. So therefore no work is done. So therefore what will happen is any work that would have been done will be converted into heat energy, which will be lost or gained. And that's primarily how we measure the energy lost or gained in a reaction. But please make sure we understand. I mean, if you throw a stick of dynamite, most of the energy is being released in the form of work, not in the form of heat. So a lot of times we'll refer to these as being kind of equivalent to each other, but that's given the assumption that there is no work being done. For now, I'm going to focus on delta E, and I'm going to come back to delta H. So right now in this video, I'm going to focus on this, and then later on we're going to focus on all these different ways we calculate delta H and how calorimetry works so that we avoid work, basically. That's what we're really doing. If we wanted just an easy way of measuring energy, we avoid work. Work is more difficult to measure than heat. All right, so couple of quick reminders. These diagrams, for those who don't remember, are endothermic. We know that because the products have more energy, than the reactants do. Remember where energy goes in an equation. It will be very important. They have lots of application questions. If you don't remember where the heat is in the equation, then you're in trouble. If you don't remember how things are going to feel if the process is endothermic or exothermic, you're going to lose points as well. So if, let's say, this process that's endothermic were happening in let's say a cup, and you are touching that cup with your hand, the question is, how would that cup feel? Well, the cup is absorbing heat energy, and it's converting it to potential energy. That's really important. When things absorb heat, they don't actually feel hot. What you would notice is the heat is leaving your hand. Your hand is what we call the surroundings, and it'll be entering the cup, which would be the system. And since heat would be going like this, heat going into the cup, the cup would actually feel cold to you because your hand would be losing heat. Another important point here is where the energy term goes in the equation. It's going to go on this side here. And for those who remember, whenever something is endothermic, the delta H is always going to be a positive value. And you can think of that because the system is gaining energy, and that's why it's positive. So that's your really basic thing. On the next slide of this video, I'm going to talk about the components of delta E. But the big introduction is, if it's endothermic, it feels cold, the energy is on the left, and the delta H is a positive value. If it's exothermic, the diagram is reversed. Your potential energy looks like this, right? Your products have less energy. Energy is being lost. If you would put your hand on a system where it's exothermic, it would feel very hot. Sometimes so hot that you would burn yourself, so you wouldn't put your hand on it. And all these places, like where this goes, this value here would be reversed. So the delta E, energy lost or gain, has 2 components, and sometimes the 2 components are inconsistent. The 2 components are Q, which is basically heat, and W, which is work. both of which can be measured in joules because they're a form of energy. Heat's a form of energy, and work is mechanical energy. So imagine you have a system like so. Here's your system, right? And the system, let's say, absorbs 20 joules of heat during a process. But at the same time, okay, the volume expands and it pushes, okay, against the external surroundings, which means it does work on this, it expands, and therefore there's work being done on the surroundings, All right, so here's the idea. Basically, when you absorb heat, that means energy is coming into the system. But if you do work on the surroundings, that means energy is going out. So if we're doing, let's say, 30 joules of work on the surroundings, right? Well, here's the thing. We're gaining energy, that's positive, but we're losing energy when we do work on the surroundings. I mean, we're pushing stuff there. So the stuff that moved, we're transferring energy to the surroundings. So this is actually negative. And what that means is the system is losing that energy. So in this particular case, overall, when we figure out what delta E is equal to, okay, Q plus W equals 20 joules, I think, right, plus negative 30 joules, which means overall the value for delta E is a negative 10 joules, which means overall this process is exothermic. Make sure we're clear. The only way we're doing work, by the way, is the evolution of a gas, okay, which expands the container. Okay, any explosive you've ever heard of, okay, that release energy in the form of work, basically do it by turning solids or liquids into gases which expand and blow stuff up, right? So let's take a look at a couple of situations here. Let's say we have a situation where both Q and W are being done on the surroundings. What this means is we have energy leaving in the form of Q. So let's say this is like 10 joules going out, and let's say we have 30 joules of work being done on the surroundings. Well, in both these cases, energy is being lost by the system and being given to the surroundings. So in this case, it would just be 10 joules plus 30 joules gives you 40 joules, and knows the positive values. Okay, I'm sorry, this being lost, so negative and negative. My mistake, right? Because we're losing energy to the surroundings, and that means this is negative 40, and this is our delta E, okay, overall, which would be equal to delta H, by the way, if this was done in a constant pressure calorimetry situation. All right, you can have a situation in which both arrows are going in. Make sure you're clear. If this is happening, it means okay, the system must be expanding, and the way we expanding, this would be work done on surroundings. Let's talk a little more about work. So if you have a system inside of a closed container, let's say it's in a piston that can move up and down like so. That's my worst piston ever. All right, and let's say this is their system in here, right? And let's say if let's say you started with 2 moles of gas, but you're in the process you're making more moles of gas, then what's going to happen is this piston will move up and push against the surroundings. So basically, if the volume expands, right, you're doing work on the surroundings. If the volume were to get smaller, the surroundings are doing work on you. Well, how can we quantify that? Well, it comes down to just a really simple physicsy substitution here, right? If you think about what pressure is, okay, right? So pressure, okay, is essentially equal to a force over a distance squared, right? And if you think about the change in volume, the change in volume is going to be the units for the change in volume. We really only care about the delta V, not what the original V was, right? It is really going to be a distance cubed. So clunk, clunk, we end up force times distance, right? So essentially what we can do is we can do a quick substitution. We can say work is equal to the pressure times the change in the volume. Now we want to make sure this works in our equation, right? So what we make the substitution, we go delta E is equal to Q minus P delta V. And what this means is if the volume, if this expands, right? If we get a greater volume of our system, right? So that's our system that's expanding. That means we're doing work on the surroundings, and we want to indicate that's exothermic. So we have this negative here, And the negative makes sense because that will make the value of delta E negative as well. So if we have a system like this, we start like this, and we're giving off 20 joules of heat, right? And our system is actually getting larger as well, so we're also expanding, and the value of P delta V ends up being equal to, let's say, 10 joules. Well, because of this negative here, it will work in the equation. So we'll get 20 joules minus 10 joules, and this would be -2, and then we get -30 joules. A quick, really important fact here, which I'm not going to do a problem on, though, is it turns out that 1 ATM times 1 liter is equal to 101.3 joules. So if they ever ask you to figure out how much work is being done, you can literally plug this information in there. Okay, so if they give you volume, get it into liters, get the pressure into atmospheres, and you can convert, and whatever number you get, multiply that by 101.3, and that will give you the number of joules. You can use that as sort of a factor. So 1 liter atmosphere is equal to 101.3 joules, and you can add them together.